let's go back to 2 dimensions and we'll start talking about a really practical device, and that's a capacitor. That's a really important electrical device. If you look at any kind of electrical object you have, TV, computer, microwave, anything like that, there will be a sticker on there somewhere that will say, do not open this device, not even if it's unplugged. The reason for that is that inside your device, and I'm going to be a little bit candid here, I opened mine anyway. Inside your device, if you open it up and look, you're going to have a whole bunch of these guys. Hang on, I'm going to get it open on my laptop and hold it under the iPad. Okay, you're going to have a whole whack of these guys. What a state. These are all capacitors. So if you look inside any kind of electrical device, like even a calculator, you're going to have some of these guys inside. What they do is they store energy, and they store electrical energy. So that's the next thing we're going to look at, is what are these devices. If you're interested in the method of how they store energy, then you might be interested in Physics 2055. We do a lot about capacitors there. So what a capacitor is it's a charged plane close to another charged plane. So we have 2 charged plates and they're separated by a small distance. And the charges on these 2 plates are equal and opposite. So that's what a capacitor is. 2 plates with equal and opposite charge separated by a small distance d. So there's our separation between the 2 plates. This guy we'll say has charge minus Q. And we'll say this plate has charge plus Q. And our value of D is very small compared to the size of the plates. So for example, your capacitor might have plates that, a simple one might be a square centimeter, but the spacing between them would be, a tenth or a hundredth of a millimeter. So that's what we mean by very small. So if we wish, we can draw our pluses on this plate for a positive plate. And then our minuses go on this plate because it has negative charge. And then hopefully you're asking yourself, what does the electric field look like? Well, the electric field goes from positive to negative. It's pretty hard to draw in a 3D view, but I'll give it a shot. Goes from positive to negative, so something like this. Okay, a little hard to draw. Hopefully you get the idea. Sometimes it's more useful to have our side view. So this would be our positive plate. This would be our negative plate, and those 2 plates have a separation of D. So now the question we're going to ask, and what we're going to try and figure out, is what is the electric field in the vicinity of our capacitor? The plates are always parallel, so sometimes it's not just called a capacitor, sometimes it's a parallel plate capacitor. So what is the electric field? There are 2 spots we can talk about. We can talk about inside, or we can talk about outside. So let's think about, how do we find that electric field? We have 2 plates, so we'll have 2 contributions to the electric field. To get your total electric field, you add up the electric field from each plate. Okay, so there's our idea. We're going to call this guy plate 1. And let's remember what we said about plates. When we have plates, the electric field is the charge density divided by 2 times the permittivity of free space. So this is plate 1. The 3 spots where we might find the electric field of this plate is, we might look at it somewhere in between the plates. So there's my electric field, E due to plate 1, equals eta over 2 epsilon naught times I hat. I'm going to take my x and y in the usual way. I might look at my electric field outside the plate. There's my electric field due to plate 1. Points to the left because it goes away from a positive. So there's E1. Left means it's minus eta over 2 epsilon naught times I hat. And I might look at the electric field out here. So out here, remember I'm just writing down what's the electric field due to plate 1. I'll do plate 2 after. My electric field due to plate 1 is going to point to the right because it goes away from this positive plate. So as I'm doing this part, I can just pretend plate 2 doesn't exist because I'm not asking about that electric field just yet. For right now, I'm writing down the field of plate 1. So my net electric field that I'm trying to calculate is the sum of the electric fields from each plate. So first I'll find my E1s, then I'll find my E2s, then I'll add them up together. So my electric field right here due to plate 1 points away, so in the positive x direction. And it's E1 equals eta over 2 epsilon naught, because that's how big the electric field around a charged plane is, I hat. So things we're remembering now is that E equals eta over 2 epsilon naught. Eta is the charge density. Sometimes we might call that the area charge density or the surface area charge density. That's Q over area. And area means the area of the plate. And epsilon naught is our constant. 8.85 times 10 to the minus 12 coulombs squared over newtons meters squared. Okay, so those are my electric fields due to plate 1. What about due to plate 2? So with my plate 2, my negative plate, let's find the electric field in those same spots. So in between the two plates, my electric field goes into the negative, and it's E2 equals eta over 2 epsilon naught I hat. So these plates have the same area and the same charge, so they have the same charge density. So my electric field has the same magnitude. My electric field out in this spot goes in towards the negative, so this way. Here my E2 is, this one points right, so it's positive, eta over 2 epsilon naught I hat. Then over here in this spot, it's going in towards the negative, so E2 equals minus, because it points left, eta over 2 epsilon naught. Okay, so the result I've used here is that the electric field around a charged plate is the charge density eta divided by 2 times epsilon naught. I have 2 plates, so I'm finding the electric field due to each of the 2 plates. And next I'll find my total electric field by adding those 2 things together. So out here, to the left of plate 1, my net electric field is E1 plus E2. But those 2 guys are equal and opposite. That equals 0. Out here to the right of plate 2, my net electric field equals E1 plus E2. Again, equal and opposite equals 0 out here too. And in the middle of the plates, they both point in the same direction, so they're going to add up. So I have eta over 2 epsilon naught I plus eta over 2 epsilon naught I to give me eta over epsilon naught I. So one thing I would say to be careful of here is you're going to see the expression eta over 2 epsilon naught and eta over epsilon naught. Make sure you know what thing you're talking about. If you have a single plane by itself, then it's eta over 2 epsilon naught. When you put 2 of them together, it doubles. So that's where the 2 went. So what I wrote up here is around one plane. So that's what this information is for. And then what I have down here is the sum to tell us what happens when we put 2 planes together and make a capacitor. So our result then for what is the electric field in the vicinity of a parallel plate capacitor is that our electric field equals 0 outside, and our electric field in between the plates is equal to eta over epsilon naught. And the direction, because it is a vector, is from the positive plate towards the negative. Okay, next we'll take a quick look at the difference between a real capacitor and an ideal capacitor, and then we can do some examples.